And then the next we have Dajun Zhang from the University of Wisconsin-Madison, who will be giving a presentation on remotely moving objects underwater using sound. That one is this one. All right. Thank you so much.
Hi everyone, my name is Dajun Zhang. I'm from University of Wisconsin. From University of Wisconsin Madison, and I'm a PhD student, and my supervisor is Professor Chuma. So today I will introduce you our recent research about using metamaterial to realize large object manipulations. And this picture is a commercial underwater robots. So as you can see, it looks bulky and cumbersome. So one reason of that is it's need a very long cable connection to outside, such as a boat or machine to power the robots. And another reason is it needs very complex, very big motor and motion control system. And because of that, it's also difficult to realize very complex motions of these robots. So we want to use acoustic way to realize the control of such large robots or machines. And our method is use lightweight metamaterial to replace the battery and motors. And here is a picture of our approach. So the transducer will emit a wave and it goes to the metamaterial, and the metamaterial will reflect the wave. And then there will be a acoustic radiation force generated on the metamaterial. And after, so the black one is a metamaterial. And after we fix the metamaterial on the large object also have a force. So we realize a force control on the large object. And we use the soft lithography of iron resin mixture to fabricate the metamaterial. Compared with the reported method, our method has some advantages. It has high acoustic impedance contrast with water, and also the fabrication resolution is very high, and the method has low cost and scalability. And we also design different metamaterial to realize different moment control of the object. For example, this one is a pushing metamaterial. It will push the object moving, have a translation moment. For example, in the picture, it's how the object is moving to right after we have a acoustic beam in, and this is a rotating metamaterial. The center row is a rotating metamaterial. It will rotate the object, and the last row is following metamaterial. So the object will follow the moment of the ultrasound beam, so it will have a S-shaped trajectory. And we also design to make the metamaterial multifunctional. So we have several methods. First method is spatial superimposition. So we overlap the different functions together. So as you can see, the object will not only have a pushing force, but also have a rotating force. So it will have a curved trajectory. And the second line is frequency multiplexing method, that the metamaterial can have different force when the input frequency is different. For example, for 1 MHz input, the object will move to left, and for 3 MHz input, it will move to the right. And we also realized a very interesting video for complex manipulations. So the first one is multi-object manipulation. So those two objects are individually controlled, and the left one is rotating, and they are merging together by control of two transducers movement. And this one is multi-pass manipulations, And this object have two metamaterial on its bottom, and they have different functions. And we control the object movement by different input wave positions and different frequency. So at first it goes straight, have a straight trajectory, but after we moving the transducer position, it has a curved trajectory. And this one is a non-invasive manipulation inside the tube. So we realize the movement of the small object in tube by the ultrasound, and this object have a pushing metamaterial at its bottom. So it's very this tube is very similar to our blood vessel. So probably we can realize the control inside the blood vessels. This is a 3D manipulation experiment, and this object has three metamaterial at its bottom, and we realize moving upward and downward by using different power, and we also realize the moment of the object translation, left and right translation by moving the transducer positions. Our method is a non-invasive manipulation method, and we realize a remote control. And control has high spatial resolution, and it has multiple degree of freedom. It may have many applications. So, for example, underwater vehicle movement, underwater robots control, and surgery robot or drug delivery, and additive manufacturing. Thank you. And if you are interested, I welcome you to my technical sections in this afternoon.
Thank you so much. So before we start with some online questions, I have another question.
Okay.
So you talked a little about how you fabricated the material. Can you talk a little bit more about maybe the trial of that process and choosing the materials for it?
Okay. So for the previously reported method, most methods use a bulk metal or air bubble or ceramics. But they cannot realize our advantages. For example, very high fabrication resolution and very low cost at the same time. And our method is use iron resin mixture, and we use 3D printed base and fabricate a soft mold, and then fabricate our metamaterial, so it can realize this advantage at the same time. So
Thank you. We'll get some online questions now.
All right, thanks for the presentation. Our first online question is, what is the largest object you've tested the technique on? Can it be used to salvage sunken items? And this is from Anashay Bhandari.
Okay, so for previously acoustic manipulation research, most research is focused on objects smaller than wavelengths. So our large or small is a comparison with wavelengths of we use. So our large object means the object is larger than wavelengths. And for our method, actually we can stick the metamaterial on any object, so it will change the radiation force. So force can be added to any objects. So in the future, probably we can realize any different material or object movement. So we just change the force on the object.
Got it, thank you. And one more question. This one is from Avery Thompson. Avery asks, are there other types of metamaterial designs you're considering to add additional functions?
Yeah, that's a very interesting question. So for this project, we just probably start the research about these directions, and in which but metamaterial is very powerful. It has many reported research. So it can be very multifunctional, but for us, we just realize it. And in the future, we can fabricate or design many complex or multifunction metamaterial, and it is possible to realize many interesting functions.
All right. I think that's it for our questions. Thank you again for your
Thank you.
presentation.